So now let's define the computational complexity with respect to the input sample size n. We can make a very simple algorithm that does not use any training data. That is the problem for this question, computational complexity with respect to the number of training samples. One very naive training algorithm is just say, okay, no matter which training data we have, let's say this area is positive area and this area is negative area. This is also learning. Okay, nobody can say this is not training process. And this training process require basically zero computation. Okay, so well then the computational complexity is O over 1. That's it. But the problem is of such approach is the quality of the output, the error rate of the output. Okay, so we have to consider the learning performance as well. So to define computational complexity of a learning algorithm, we have to define performance constraint. Okay, so we have to say the computational complexity to make epsilon accurate algorithm with probability 1 minus delta. Okay, that is the right definition for the computational complexity of learning. And there is another issue. We can make some very bad cheating for this computational complexity. Okay, what is the cheating? We can defer all the computation to the test page. Okay, so we can make very simple training algorithm, but to make the output from the model, we need a lot of computation. Right? So, for instance, when we make a ERM loop, we have we can make very easy hypothesis, so that we can very easily discriminate the best hypothesis among our hypothesis class. But it is possible to make a decision from the obtained hypothesis. Is very complicated. It is possible. Okay, we can design some training algorithm such that the training page is very easy, but the test page is very complicated. But the question is, if we only care about the training complexity, this approach, very easy training but very complicated testing, this approach is very simple algorithm. The computational complexity will be very low. But in practice, we don't want such algorithm. We want both the training and test computational complexity is limited. We want to make both complexities low. Okay, so we need consider both training complexity and test complexity, and in many cases we make constraint so that the computational complexity of training page is higher than the computational complexity of test page. Okay, so this is the formal definition of computational complexity of learning. So we basically can define the learning complexity in two steps. The first step is for the single hypothesis class. Given a function f, a learning task, so this is the input domain hypothesis class we are considering, and this is the root function. And a running algorithm A, we say that the algorithm A solves the running task in time order of f if there exists some constants C such that for every probability distribution D, data generation distribution D over the domain Z, and input epsilon accuracy with probability 1 minus delta when A has access to samples generated IID by D. Training complexity is A terminate after performing at most C times F epsilon delta. Then we say, okay, our algorithm computation complexity order is at most F. Okay, from the definition of big O notation. And here one remark is we don't say anything about the training set size. We just say, okay, we can generate training data sample as many as we want from the data generation distribution D. So this is training complexity from the beginning of training to the end of training. And test complexity is the output of A, HA, the hypothesis A, can predict the label of new example with at most C times F epsilon delta. So this is at most, so which means both training and test page complexity are limited by the function f times some constant. Okay, and also this is very important. We have to consider the performance as well. So the algorithm training and test process satisfy this performance constraint. The loss function, test loss function, is bounded by the best test loss plus epsilon with probability 1 minus delta. So this is agnostic pen learning constraint. So we can extend this definition to sequence of learning model. So there is sequence of input domain, sequence of hypothesis class, and loss function defined on the domain and hypothesis class. Okay, and let A be a learning algorithm designed for solving such a learning sequence problems. Given a function g, so here there is an additional integer term here to denote the I, the problem index. We say that the runtime of A with respect to the processing sequence is O of g. If for all I, the algorithm A solves the problem in time order of gi epsilon delta. So the definition 8.1 is not only defined for just one single training scenario, but also defined for the sequence of training scenario. So what's the meaning of efficient algorithm for this case? When G can be a polynomial, so here polynomial is very important. So we don't want exponentially growing case, because exponentially growing case, the increased speed is super fast, and with some moderate size of data, it can be disaster, even with moderate size. Okay, so we want to make a polynomial time algorithm with respect to the task index I and 1 over epsilon and 1 over delta. That is what we want to show in most of case. Okay, so let's go back to the ERM rule. So what was ERM? ERM rule was given a hypothesis class H, a domain set Z, and a loss function L. The corresponding ERM rule can be defined as follows. For any given input sample size, samples set S, we find the best hypothesis among our hypothesis class that minimize the training error. So this is definition of training error, and we want to make the best hypothesis. We want to find best hypothesis that minimize this training error. So one very straightforward idea is exhaustive search. So test every hypothesis in our hypothesis class. So compute all the training error for each hypothesis in our hypothesis class. Then, so what is the computational complexity for this ERM rule? First of all, what is the sample complexity? We require this amount of sample to guarantee epsilon accurate and delta 1 over delta probability from the agnostic packed learning theorem. And all the hypotheses have to evaluate the loss function of a whole training data point. So the computational complexity to test one single hypothesis is proportional to the sample complexity. Okay, and if LHZ, the loss function, require k number of computations, then the training complexity is k times the hypothesis class size, because we have to test every single hypothesis with every single training data point. So this amount of computation we need, and we need this amount of computation to test one single data point. So the total training complexity is this. So it looks like, okay, this looks like polynomial, so yeah, this is good to say, very nice algorithm. But the problem is the cardinality of hypothesis class could be huge. In some case, even this is exponentially grow as the index grows in the previous page. And in some case, the hypothesis class has infinitely many different hypotheses, right? So what if the hypothesis size is huge? Then there is no way to find the ERM solution in polynomial time. Can we design efficient algorithm for ERM rule with huge hypothesis class? Can you say yes? That is very, very important question.